G'day, my name is Dr. John Steele, the University of New South Wales in Sydney, Australia. In this video I'm going to talk a bit about drawing and sketching in 3 dimensions, giving you some tricks and tips, simple things that might help you draw slightly better diagrams for your multivariable calculus course. I'm going to split what I'm going to talk about into 2 halves. In this first half I'll talk a bit about basics, and drawing planes and spheres. In the second one I'll talk about drawing more general surfaces of the type that you typically get asked to do. So, first and most basically, use a pencil. You're going to make mistakes, you're going to want to turn solid lines or curves into dashed lines on curves, and you can do that with a pencil that you can't do with ink. Don't try and use ink and correction fluid, that just makes your diagram look a complete mess. Use a pencil. For straight edges, straight lines, use a ruler. Doesn't have to be a ruler, of course, it could be part of a set square, something that's going to give you a good straight edge. You don't have to do that, but it does make the diagram look a lot better. When drawing curves, let me suggest that you try and draw curves with your hand on the inside of the curve, not the outside. If necessary, turn the paper round. It's always much easier to do that way. It's a trick I picked up back when I was doing technical drawing in high school. One of the things you're trying to do in these sketches is to suggest to the eye what's going on. This is why if you've got a curve that's hidden behind a surface, you would tend to put it as dashes or dots, typically dashes if you're doing it by hand, of course. And why if you've got one curve in front of another, you tend to break the curve to suggest that it is behind. Here's an example. Here's a curve, AB, and here's a curve I want to suggest goes behind it. That's why I've broken the line. It suggests to the eye that CD is behind. So the last little thing I want to talk about under basics is perspective. It's usual to draw a curve or a surface in 3 dimensions anyway as if it is below you and to your left. Why that is, I don't actually know. I suspect it's something to do with the fact that we use right-handed axes, and when you've got a number line, you number the line increasing to the right. Again, it's not something that you have to do, but if you look in some textbooks, I think you'll find that's what most of the diagrams draw. So that's what you would tend to do anyway, even if you didn't think about it. And the other thing you should remember is that if you've got 2 lines that are at right angles, unless you're looking right down on them, then they will not be at right angles in your diagram. It's particularly important with axes. I'll talk a bit about that in the next little section, but it applies to other lines as well. And it applies to things like circles. A circle will tend to look like an ellipse unless you're looking straight down on it. So if you're going to draw something that's a circle but you're not looking down on it, draw it as an ellipse. Spheres always look spherical, they're always round, but circles are going to be elliptical. I'll talk a bit more about drawing spheres at the end of this video. So, axes. I'm talking about Cartesian axes here. Cartesian coordinates, we want 3 mutually perpendicular lines in space to define the axes. X, Y, and Z typically. What you should be aware of is that if you do have 3 lines that meet at right, mutually orthogonal, meet at right angles in space, then when you draw them or you look at them on a picture, then they are not at right angles. And you can see this yourself. Take your phone out and take a picture of the corner of your room, and unless you've got one of these rooms that's been designed by some crazy architect where everything is at weird angles, then the corner you'll have will have 2 walls and a ceiling meeting at right angles. This is a picture of such a corner in my room. It's actually a beam going across my office. And you can see there's 3 mutually perpendicular lines here, the vertical line and 2 horizontal ones, and they're not at right angles on the picture. If you lay a piece of paper along, say, the vertical line, the edge of one piece of paper with a corner of the paper at the corner where the lines meet, then the other edge of the paper does not lie along the ceiling line, the line where the ceiling and the wall meets. Then not at right angles on the page. Similarly, if you look at what a computer package does, a proper computer plotting package does when it draws axes, it doesn't draw them at right angles on the page either. This is a screenshot from GeoGebra, and as you can see, the red axis and the blue axis are perpendicular. The blue axis is meant to be the vertical one, the z-axis. And the other horizontal axis, green, is hidden. It's covering or covered by the blue one. So what I'm getting at is that when you're trying to draw something in 3 dimensions, don't draw something that looks like this. That you'll never see. right? Draw something that actually got an attempt at least at what perspective would look like. I should also point out, by the way, make these apparent angles reasonably large. It just makes life a bit easier if you do that. And the last thing I want to say about axes is, although it is traditional to have the z-axis as the vertical axis, it doesn't have to be. Sometimes it's easier to draw your diagram and have the y-axis as vertical. If that's the case, just label the y-axis as the vertical axis. Just try and make sure you label them properly, and try and make sure you get them right-handed, not left-handed. Use the right-hand rule, x, y, z. Right? If this particular set, for example, if that is meant to be the y-axis, because that's easiest, then that's to be y, x, y, z. This would be x increasing this way, and this would have to be z. So that's the correct way of doing it. It doesn't often matter that if you get this left-handed instead of right-handed, but particularly if you're doing a course in vector calculus, there are situations where it does matter. It does matter that you get your axis in right-handed and everything going in the right direction. So better to get it right all the time than worry about whether you have to get it right or not. Planes. How to draw a plane? Well, I'm going to give you two examples here. To the standard ones you have to draw planes that intersect one axis and therefore parallel to one of the coordinate planes, and planes that intersect all three axes. Firstly, planes that intersect one of the coordinate planes, so are parallel to, intersect one of the coordinate axes or parallel to one of the coordinate planes. This is really quite simple. Once you've got your axes, you basically just draw a big parallelogram with your edges parallel to appropriate parts of the appropriate coordinate axes. Technically, it shouldn't be a parallel. These parallel lines ought to converge, of course, but we don't tend to bother with that aspect of perspective in mathematical diagrams because they're just not big enough. So here we go. Here's our axes, and I'm just going to draw a big parallelogram, or a reasonably sized parallelogram with axes roughly parallel. This is where using a ruler it really helps. Is that parallel? Oh, close enough. And then one parallel again, right here. And then another one vertical. There will do. Okay. Now we want to fix that up so that it actually looks like some of the axes are behind. I wanted this really to intersect the x-axis. If this is the x-axis of the front here, somewhere around here. So what I'm meaning by that is that this part of the x-axis is to be hidden. So we'll just rub it out, it's hidden. The z-axis is always hidden. There, and the y-axis as well, behind the plane. Okay. From here onwards, the x-axis is actually pointing outwards. Yep, this is to be the x-axis. I've got a little bit of extra. There we'll rub out. Now, what's going to happen at these points, I'm going to rub them out and fix them up just to make it look a little neater. This is something you don't have to do. Worrying about what axis is behind what, and here as well. This one first. In this case, the axis will be in front. So that's what I meant by breaking one line hidden behind. In this case, the plane is in front. That would go like that. Remember, it's meant to be the y-axis, z-axis here, and again, in this case, the plane is in front, break the axis. In this case, the plane in front, break the axis, sorry, and in this case as well. And what's happening down here? Well, the plane is in front of that axis too. So that gives you the idea that this plane is meeting the x-axis here, with the coordinate axes behind it. So what about a plane that intersects all three axes? Well, in this case, the first thing you would do is you would pick the intersection points. You've got the coordinate, you've got the equation for the plane, so you pick the coordinate points where it meets the coordinate axes, and you'd note them in. Then what you do is again, don't forget pencil and lightly, you'd join these up to form a triangle. This is actually a little better done with a ruler. Like so. You then extend that triangle to be some sort of parallelogram. Now there are several ways of doing this. You want to make sure that none of the edges of the parallelogram are actually perpendicular, or parallel I should say, to any of the coordinate axes. So I think one here would probably be the right way of doing it. Like that. Will do. You extend that to parallelogram. Now you don't need that line, so you can get it out now or later, doesn't matter when. Then you take that parallelogram and blow it up into a bigger parallelogram. Again, making sure you've got enough room to do it, and paying attention to where these lines are going to come. And I think here, and somewhere here. I think I'll have to do it about there. Right, join it up that way. And that's our basic plane. Now you're going to start correcting that. You don't need this anymore. We don't need that anymore. We don't need this bit. That line's going to become dashed in a minute anyway. We'll still need those contact points. That. And then you work out which axis is which. I've not put them in, but we'll put them in now. X, Y, Z. And I think we're having the Y axis is behind here, and then it's in front from there onwards. So we're going to have to fix that up. It's going to be behind up to that contact point, and then in front, behind here. It's behind the plane. The Z-axis, that is behind the plane up to there, and then in front. So we have to sort that out. And in this case, the Z-axis is in front here. The Y-axis in front there. The X-axis in front here. And plane is actually in front here. I should have dashed that axis as well. And in front there. There we go. And that's our plane intersecting the three axes at the various points. You then put in what these numbers happen to be, whatever they are. I don't know, 4, 3, 7 or something like that, and maybe that's not such a great choice. Then you'd have to say, okay, well, what is that curve, that plane? That's the plane x plus y. I'll have to put numbers in here, equals 7, 3, 4. So these common multiple of that, 84, isn't it? Yep. So if it's intersecting z at 7, then that should be 12. This one should be 21, I think. No, that one should be 21, and this one should be 28. Not such a great choice of numbers there, but that's what that plane is with the various intersection points. So, spheres. As I said earlier, whichever way you look at a sphere, it looks circular. So that's how you draw it. And this is the big tip, draw the sphere first. In fact, that applies in the next section too. Draw the surface first, put the axes in afterwards, manipulating them or rubbing them out if necessary. So if you want to draw a sphere, that we begin by drawing a big circle. You don't have to use a set of compasses. I'm just going to draw a circle freehand and hopefully get something reasonable. Right, so this is going to be our basic sphere, and I'm going to indicate that it's round by drawing in an equator, which will be more or less an ellipse. And since the back half of the equator isn't seen, I'm going to draw that in as a dashed part of an ellipse. So that suggests to the eye that what you've got is something spherical. And then you put the axes in. Now, the next question you've got to face with is where's the centre of the sphere in relation to the origin of the coordinates. I'm going to assume that it's at the centre, right? The origin of the coordinates centre of the sphere. It doesn't have to be, of course. And then you draw in your axes, vertical, and you might as well draw them in dashed here because you're putting them in hidden. Z-axis here, up and down. Let me point out, by the way, that the North Pole, the topmost part of the sphere, will actually be about here. It won't be at the top. It's a fine detail that probably isn't important whether you get that right or not. And then the x-axis, say, coming out here. Well, where will the x-axis meet the sphere? Of course, it will leave it at the equator, so from there onwards it should be solid. And going back, hidden until you get to there. And then the y-axis at some suitable angle here. And again, the y-axis will leave the sphere at that point there. So there's my sphere. That's the point at which the z-axis will leave the sphere. This is the point actually on the equator where the x-axis will, and there's a point here where the negative y-axis leaves the sphere. Now if you wanted to make this look a little neater, you could start hiding lines here and there and up here and so on. I'm just not going to bother doing that here. Not usually necessary to make that sort of fine detail. But if you wanted something to look pretty, that's what you would do. Thank you.